Okay, any question? No. Okay, in the videos of which one? V6, V7, V8, and V9, the subjects of maximal ideals, prime ideals, and what? Polynomial rings, I think. Polynomial rings are covered. So let me first give you the basics about this, okay? So first, what a maximal ideal is. Definition. Let R be a ring with identity. Do you know the definition? Identity means that the multiplicative identity, or in some texts you can see it as unity, not unit, but unity. It means that multiplicative identity of the ring. And unit is another thing. Let me put it here. Unit is invertible element. An element which has a multiplicative inverse. Unity means that multiplicative identity. Okay? Maybe you follow some other books, so you can see this word also for the multiplicative identity. Now we have a ring with identity, and we are going to an ideal M as maximal ideal. An ideal M is maximal if there is no intermediate ideal between our ideal M and the whole ring. There is no intermediate ideal between M and R. Or equivalently, you can say that equivalently. If you have an ideal between these two, then this means that this intermediate ideal I either equal to R or it is equal to our ideal M. Okay, so if you have a question asking you that show that some kind of ideal with some given properties maximal, then you are going to assume that there's an ideal in between your ideal given and the whole ring, and you're going to show that that ideal has to be equal to your given ideal or the whole ring. Okay, just applying the definition. Or we have something like this as a theorem. You can also use this one. M is a maximal ideal of R. Of course, here we have R is a commutative ring with 1. It is not necessary for the definition of a maximal ideal that R being a commutative ring with 1, but for this theorem we need this commutative ring with 1. 1 means that, again, multiplicative identity. And this is different from 0, the 0 of the ideal, additive identity of the ring. And now if you have a commutative ring with 1, then you can say that M is a maximal ideal of R if and only if you think of the quotient of your ring R with respect to not I but M. If this is a field, then you can say that your ideal is maximal. Okay? You can use either, while approaching a question, you can use either directly the definition. That this means that take an intermediate ideal and show that it has to be equal to your ideal or the whole ring. Or you can look at the quotient of the ring with your given ideal and see that that quotient is a field. And this is a two-sided implication. So this means that if you're given a maximal ideal, then you're sure that the quotient is a field. And the other way around, if you have a quotient which is a field, quotient ring which is a field, then you can say directly that the ideal that you're taking the quotient is a maximal ideal. So you can use each sign, okay? So, for example, considering this one, should I do this? I don't know. Maybe after, okay, this one, for example. An example from recitation notes. Let R be the ring of all continuous functions on the interval, on closed and bounded interval 0, 2. Okay, you can check that this is indeed a ring. Okay, with pointwise addition and pointwise multiplication. Now, let me give you a subset of it. Consider the subset. Subset I of R given by I contains all functions in R such that the function value of these functions at 1 is equal to 0. Now, our aim is to show that I is the maximal ideal. Okay, now how to show that? I'm not going to use the definition, but I'm going to use the theorem here. Somehow I'm going to write down, okay, I'm going to try to write down a map and with quotient this I, and at the end, the quotient will be isomorphic to a field, okay? Let R be the ring of all, let me write real values. No, okay. No, real values is not necessary because I defined the interval as 0, 2. Okay. Now, what to do here? Well, let us first show that I is an ideal. How to show that a subset is an ideal? First, we need to show that it is closed under addition. And then we need to show additive inverses. And at the end, we need to show that it is closed under multiplication with an element from the ring R. Okay, now let us start. Where are you? Okay, let us start. Okay. Let us take F and G from I. With these, for these two conditions, we can just show that if you take two elements, either you can show that F plus G is in I and minus F is in I separately, or you can directly show that for these two elements, we can show that f minus g lies in I, and this difference covers these two conditions, okay? Now, what does it mean, being in I? The definition of I is this one, and this means that you're putting some functions inside this I, and these functions have the property that their function values at 1 has to be equal to 0, okay? So, showing that f minus g is inside I, this means that i.e. f minus g evaluated at 1 has to be equal to 0, okay? This is just a definition of our subset I, right? So, let us look at f minus g evaluated at 1. And this ring, the addition of this ring is just component-wise. Just you're adding the function value or multiplying the function value. So this means that f minus g evaluated at 1 means that this is f of 1 minus g of 1. And we know that since f is taken from I here, we know that f of 1 is equal to 0. And since g is taken from I, this means that g of 1 is equal to 0. So at the end, the function value of this f minus g evaluated at 1 is equal to 0. And this means that f minus g satisfies the definition of I. So f minus g lies in I. Okay? Now what about multiplication? Let us take an arbitrary function from R and a function from I. Okay? Yes. Now, to see that, we need to show now h of x times f of x, or h times f, lies in I. And this means that, instead of this one, let me now change the notation, h from R and f from I. We need to show that h times f is in I. And this means that hf evaluated at 1 is equal to 0. As I said, the multiplication is also component-wise. So this means that hf evaluated at 1 means that h of 1 times f of 1. And here we know that f is taken from I. This means that f of 1 is equal to 0. So this is 0. And 0 times something in real numbers gives you 0. So this means that the function value of h times f evaluated at 1 is equal to 0, giving you that h times f lies in I, and hence I is an ideal. I is an ideal of R. What about maximality? For maximality, let us consider the map phi from our ring R to real numbers, okay? Taking a function, a continuous function on, if you remember, R containing all functions from 0 to R, and f is continuous. Okay, I'm taking a function and I'm evaluating it at 1. Why is that so? Because this this f of 1 that we are setting a new map, and we are defining the image of a function as its function value at 1. But why is that so? Because we want to relate this function with our given ideal, okay? And we know that this ideal contains such functions whose function values evaluate at 1, right? So this means that to relate the ideal with with our ring and with our need-defining math, we need to use the function values evaluates at 1, okay? So I'm taking a function and evaluate it at 1. So check that. Do you want me to check that this phi is a homomorphism? Huh? Is it okay for all of you? Let me look at chat. Okay. Now I think that it is all okay for you to check that such a map, okay, such a map is a homomorphism. So now we need to look at the kernel. So it is not an empty voice that saying us that we find this function related to the function values at 1. This means that we are thinking something like hope to finding kernel as our ideal I. Okay, so let us look at kernel of phi. Okay, this means that we are gathering all functions from R such that phi of f of x is the zero this range ring. And this range ring is the real numbers, and the additive identity of real numbers is 0. So this means that the image of function has to be equal to 0. But what is phi of f of x? Phi of f of x is nothing but f of 1. F of 1 is equal to 0. But what is this? This is exactly the definition of our ideal. This is I. Okay? So, after finding kernel as our given ideal I, we demand to apply the first isomorphism theorem, right? Because we are going to obtain a kernel, and in the range we have a field. But before applying the first isomorphism theorem, we need to check that our homomorphism is actually an epimorphism. Okay? Phi is surjective. Surjective means that for any real number R, show that for any R in R, there exists a function, f of x that we write, f of x in R, such that phi of f of x is equal to this real number R. So we need to find a function, find a continuous function defined on the closed and bounded interval 0, 2. So consider, take your function as the constant function, taking all values to R. Take f of x is equal to this one as the constant function. And we know that constant functions are always continuous. So in particular, they're continuous on the interval 0, 2. So this is an element from R, which is continuous everywhere. Continuous everywhere. And so f of x, R, lies in R ring R. So since for an arbitrary real number R, we can find a continuous function from R ring R, that the image of f is equal to R, this means that R phi is actually an epimorphism. Hence, phi is an epimorphism. Now, we have a surjection here, an epimorphism here, whose kernel is I. So now applying the first isomorphism theorem, by first isomorphism theorem, R over kernel phi is isomorphic to the range, which is now, since we have an epimorphism, this is isomorphic to R. But we know that kernel of phi is our ideal I, is isomorphic to R, and we know that R is a field. Now I'm applying the theorem. Since this quotient is isomorphic to a field, it means that this is a field, this is a field, and this quotient is a field, means that I is maximal. Okay? Any question about the definition, about the theorem? No? Okay. Now, after maximal ideal, we come up with a new definition. What, Saihan? Ask me your question. I'm waiting. First isomorphism. Okay, first isomorphism theorem. First isomorphism theorem is this. Now you have a ring. You have a homomorphism. Let R and S be rings, and phi from R to S be a ring homomorphism. Actually, there are two versions of first isomorphism theorem. One is defined with epimorphisms, directly with a surjective homomorphism, but I prefer this one. I'm going to write it down, the surjective version also. Now, if you have a ring homomorphism, then first isomorphism theorem tells you that if you divide this domain ring R by the kernel of phi, this is isomorphic to the image of R. Okay? But since we're using, in the previous question, we're using a surjective homomorphism, this means that, let me write it down, if phi is surjective, then this means that phi of R is equal to S, and R over kernel phi is isomorphic to S. Okay? This is first isomorphism theorem. Let me remind you what a kernel is. Kernel phi, with respect to, in terms of these rings R and S, I'm defining. Kernel of phi contains all elements from the domain ring R, such that the image of these elements is the zero of the range ring S. Okay, and we know that it was also mentioned in the video lectures. Very important property of a kernel of phi is always an ideal. Okay, this is important. Also, we have something, yeah, this one. Okay, now for our question, we have found that kernel here is I, and then applying the first isomorphism theorem, and here we have shown that phi is an epimorphism. So the first isomorphism theorem gives you that taking the quotient of R with kernel gives us the range ring. Okay, and since okay. Since the range ring is R here, then this quotient has to be isomorphic to R, which is a field. Okay? Is it okay, Sayhan? First isomorphism theorem. Any question? So. Okay. Mostly, we use these kind of homomorphisms, as in the previous question, to obtain ideals. Okay? We did the same thing in group theory, actually. When we are looking for normal subgroups, we look for homomorphisms whose kernel is the desired normal subgroup. And in the group theory, we also know that normal subgroups are kernels, and kernels are always normal subgroups. Okay, this is the same idea here. If you have an ideal, then you know that that ideal is always the kernel of some homomorphism, and vice versa. If you have a homomorphism, then the kernel of that homomorphism is always an ideal. Okay? So kernels are important. Now, let me, if you don't have any questions, let me continue with the definition of a prime ideal. Okay? Okay. Definition. Let now R be a commutative ring with 1. With 1 means that identity, unity, whatever you like. And this 1 is different from 0, its additive identity. Now we are going to call an ideal as prime. An ideal P is called a prime ideal. This is a little bit complicated, okay? But very similar to the concept that you know from integers. You know what prime integers are, right? The prime integers are the only ones whose divisors are 1 in itself. This is something like this, okay? We are going to call an ideal P as a prime ideal if for A and B in R such that A times B is in P. This implies that either A in P or B in P. Okay? When the session ends, we are going to have a 10-minute break. Then we are going to continue after 10 minutes, okay? Now, this is just the same idea with the prime elements in integers, okay? For example, if you consider a prime number, as an example, let P be a prime number in Z. Okay, this is 3, 5, 13, 9, what? 91 is not. 93 is not. 97, something like this. Now, for a prime, what do you say? For example, consider P divides A times B for two integers A and B. And since P is a prime, you can directly say that P divides either A or B or both, but doesn't matter if it divides both or not, okay? For our purposes, it is enough for us to show that P divides one of them, at least one of them, okay? From our knowledge about integers, we know that P divides A or P divides B, right? Just a review of our knowledge on integers. So this is just the same idea in giving a definition for a prime ideal, okay? You're taking a multiplication of two elements A and B in P, lying in P, the multiplication lies in P, if you can show that this multiplication inside P implies that one of the elements has to lie in P, then you're going to say that P is a prime ideal. But you have to do this for all possible products, okay? That is, I'm giving you a product of two elements, and you have to show that one of the terms in the product has to lie in P. If one product fails, then you cannot say that P is a prime ideal, okay? You have to show that for all possible products, either A or B lies in P. Then you can say that P is a prime ideal. For this one, let me solve an abstract algebra, an abstract question that involving both prime ideals and homomorphism. Before that, doing the same thing with doing the same thing as maximal ideals. Here, after giving the definition, I wrote down a theorem here. M is maximal if and only if this quotient is a field. We have a similar version for prime ideals, which is, do you know what I'm going to write?
With integral domains.
Yes, with integral domains. P is a prime ideal if and only if the quotient is an integral domain. Okay, and from here we can, just considering these two theorems, M is maximal if and only if R over M is field, and P is the prime ideal if and only if this is P. R over P is an integral domain. Just using these two, we can show a very strong result. Let me put a star here. Every maximal ideal is prime. How can we show this? Very easy, one line proof. We know that every field is an integral domain, right? Use the fact. You know this one, right? Every field is an integral domain. Just using this one in the theorem, now let I be a maximal ideal. Now, since I is a maximal ideal, we know that R over I is a field. And we know that every field is an integral domain. R over I is an integral domain. And this means that by using the last theorem that we stated, since the quotient is an integral domain, I is a prime ideal. Okay, just one line proof. Just set the logical consequences, set the logical sequence, and reach the conclusion. Okay? So we know that every prime ideal is, every maximal ideal is prime. Okay? What about the other side? The other side is not always correct. For this one, let me give you an example. Here. Not important. Let me put it in red. Not every prime ideal is maximal. Actually, you can conclude this sentence, this statement, from this fact. Not every integral domain is a field, right? The same idea, let me write. Not every integral domain the field. So not every prime ideal is maximal, okay? Now, if we say something like this, for example, in an examination, I'm saying that not every prime ideal is maximal. But just saying this is not enough. We need to give a counterexample for this one, okay? So let us look at a non-trivial counterexample. You always have this example, a trivial one. Consider, let us take our ring as Z and consider the zero ideal as the ideal generated by zero, okay? This is a prime ideal, but not maximal, okay? Why is this a prime ideal? Question. Why? Okay, I'm saying that claim the ideal generated by zero is a prime ideal in Z. Okay, our claim is this one, but it is not maximal. But the ideal generated by zero, is not maximal. Maximality being not maximal is the easiest part because zero is contained in, let me write it in the center here. The ideal generated by zero is contained in, for example, nz, and this containment are proper, okay, for any n different from zero. For example, the ideal generated by zero is contained in 2z, right? And 2z is definitely different from the whole ring. It does not give us all integers, right? It only gives us even integer. And we know that there are elements, infinitely many elements, different from zero. So this 2z is different from this ideal generated by zero. So we have found an intermediate ideal between the ideal generated by zero and the whole ring. This means that the ideal generated by zero is not maximal. For primeless of the ideal generated by zero, we are going to question was that this ideal generated by zero is a prime ideal but not maximal. We have shown that this ideal I is not maximal because we can find infinitely many intermediate ideals between the ideal generated by zero and the whole ring Z. Okay, what about primeness? This ideal generated by zero is a prime ideal. Why is that so? Because let us assume that A times B lies in the ideal generated by zero for A and B is in Z. Okay, A times B lies in this ideal means that AB is in this ideal means that you can write A times B as a multiple of zero, right? This is the ideal. This is the definition of a principal ideal. That this is a principal ideal generated by zero. So this means that this is zero times some n, and for some n, and this is zero because we're working in integers. So this means that A times B is equal to zero. But we know that there are no two non-zero integers whose product is equal to zero. So this means that since in Z there are no two non-zero, yes, integers x and y, such that I'm saying that x and y are different from 0, x times y is equal to 0. And this means that this is exactly what we call as an integral domain, actually. Since in z, a times b is equal to z, a times b is equal to 0, that implies that a is equal to 0 or b is equal to 0. This means that either a lies in the ideal generated by 0 or b lies in the ideal generated by 0. Okay, so we have taken an arbitrary product of two elements, a times b, whose product lies in the ideal generated by 0. At the end, we have shown that if one of the elements must lie in the ideal. Okay, so this means that the ideal generated by 0 is a prime ideal. This type of writing uses only the definition of prime ideal. Okay, or you can show it by another way of showing that. Oops. Nah, where are you? Here. Another way of showing that the ideal generated by 0 is prime is to look at the quotient. Z over the ideal generated by 0. Now, what is this ideal? Z over the ideal generated by 0 is nothing but you're dividing Z to nothing, right? Just the additive identity. And this means that this is isomorphic to Z. And Z, we know that Z is not a field, but an integral domain. Now, apply the theorem that we've learned. This means that since the quotient is an integral domain, this means that the ideal generated by 0 is prime. Okay? And you can also say that since Z is not a field, then the ideal generated by 0 is not maximal. Okay? You can show the maximality with the same logic. Okay? This is a trivial example. I'm saying trivial because we all know integers. For example, let me give you another one, which is, I think, non-trivial one. Now consider a polynomial ring. Example, a non-trivial one. Let R now take your ring as the polynomial ring whose coefficients coming from integers. This is a n x to the n, let me write, a n x to the n, a n minus 1 x to the n minus 1, blah, blah, blah. At the end, we have the constant term such that each ai comes from integers. Okay? This is a ring. We know that with respect to usual addition and usual multiplication. Okay? Now, consider an ideal. Consider I, the ideal generated by x. Okay? Is it a prime ideal? First question. Is the ideal generated by x a prime ideal? This is our first question. The second one is it maximal? What do you think? Is it prime or maximal? Or both? We don't know. Any suggestion? No suggestions? Let me put this up here. Okay. For example, it is a prime ideal. Why is that so? Do you want me to use the definition of a prime ideal, or do you allow me to use the theorem about this quotient thing and integral domains and prime ideals? Which one do you prefer? The definition directly or the theorem? Which one is the theorem? Okay. Question 1. Let us solve it. Now, consider the ring homomorphism phi from our ring Zx to Z. Okay, taking a polynomial a(n)x to the n, blah blah blah, a1x plus a0 to a0 to its constant term a0. Why is that so? Let us consider the logic behind it. Okay? Now, what is the ideal generated by X? This contains all elements of this form. Some function, some polynomial from the ring f of x times x, right? Not r, that's x. The ideal generated by this one is f of x times some x. And if you consider such polynomials, these kind of polynomials does not have constant terms, right? Consider this one. Let f of x a(n)x to the n, something like a0. And if you multiply these two, this means that you have a(n)x to the n plus 1, blah, 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 a1x to the a1x squared plus a0x. These kind of polynomials does not have constant terms. So this means that the homomorphism that we are going to try to write down has to do with constant terms, okay? Because this element x, this ideal generated by x, kills the constant terms. And kills means that you're taking the quotient, okay? Because taking quotient means that actually you're dividing your ring into equivalent classes with respect to the given ideal, okay? So to obtain as a kernel my ideal generated by x, I have to get rid of the constant term because my ideal generated by x does not have any constant terms in the polynomials that it contains. Okay, so here what I'm doing is that I am just sending a polynomial to its constant term. Okay, now check that this is just an explanation. Okay, let me write it down also in words. Elements in the ideal generated by x do not have non-zero constant terms. Okay, so somehow I'm trying to catch a relation between the ring elements, the elements coming from Zx, and my ideal generated by x. Okay, so let me leave you this as an exercise. Check that phi is a homomorphism that you're going to show that this function preserves the addition and the multiplication inside the rings. So let us look at the kernel of this function. Kernel phi contains all f of x in Zx such that phi of f of x is the additive identity of z, which is 0, the usual 0 that we know. So this means that this f I'm going to use as a general expression, a n x to the n, blah, 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 a0, such that the image of such a polynomial is just its constant term. A0 is equal to 0. And what does it mean? It means that you're left with the elements of the form an to the xn plus an minus 1 to the xn minus 1 dot 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 a1x, such that each ai comes from z. Okay, and if you take these type of polynomials in x parentheses, an x to the n minus 1 blah 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 a times x, such that each ai lies in z, this means that since ai's are arbitrary, this type of expression gives you an arbitrary element from R, right? So this is zx, and it is arbitrary. So this means that you have a polynomial times x, which is exactly the definition of the principal ideal generated by x, right? So this is the ideal generated by x. And as in the previous question that is related to the continuous function on the interval 0, 2, for any integer that you take from this range z, you can define the constant function, the constant polynomial, right? So it is projective for every n in z, the image of, say, f of x, and just to be the constant function n, and then phi of f of x is equal to n, means that phi is projective. Now what is left is to apply the first isomorphism theorem. Okay? Now here, apply first isomorphism theorem. We know that kernel phi is just the ideal generated by x, and phi is projective. This means that if you divide z of x by the kernel, this is the ideal generated by x, this is isomorphic to your range, okay, which is z, since phi is projective. But you know that z is an integral domain. Now apply the theorem. This implies that the ideal generated by x is a prime ideal. There's some enlightenment. Okay. Since the quotient is isomorphic to an integral domain, this means that the ideal that you're taking the quotient has to be a prime ideal. Okay. Now, the second question was that. Now, the answer for the first question is yes. We have shown that. What about the second one? Is the prime ideal? Okay, Özde. This is the prime ideal. The second question is that what about this ideal is maximal or not? But we have one question that how to choose such a homomorphism, right? Because it is something like flying map, and we are taking one of them. But it is not. Actually, the motivation in choosing such a map between z of x and z depends on this one. Now you know that. No, I need this one. Okay, the ideal generated by X is defined to be like this, right? And we have seen that these type of polynomials does not have constant terms. Okay, so to obtain to write down a homomorphism, we somehow know to set a relation between a homomorphism and your ideal, you need to use the definition of your ideal, okay, the given ideal, because you are trying to reach this ideal, right, as the kernel. Because you know that you decided that you're going to use this theorem, I is prime if and only if R over I is integral domain, right? So you know that you should write a homomorphism from your ring R to somewhere, but you're sure that your kernel is going to be I. You're going to try to define such a homomorphism, okay? So since you want kernel to be equal to your ideal, you need to consider the definition of your ideal while setting up a homomorphism. Okay, so in this example, you know that the definition of your ideal gives you polynomials with no constant terms. Okay, and as I said before, taking quotient means that at the end, by using the homomorphism, we are going to take the quotient of our ring with the kernel, right? And we want that kernel to be equal to our ideal, the ideal generated by X. So this means that dividing the ideal means that actually you're somehow killing the constant terms, because here we know that in our ideal we have no constant terms. Okay, so since we have no constant term, in defining the ideal, first consider a general form, a1x, a0. Now you don't want this a0, okay? You want this to be killed by the ideal, to be killed by the kernel. So I'm taking this one, this general element, to just a0, because I know that the remaining part, if there's a remaining part in your definition, the remaining part must lie in my ideal generated by X. Okay, so I want this one, but I don't want constant terms, because the definition of the ideal tells me that. Okay, so since I'm taking an arbitrary polynomial to its constant term, and constant term lies in Z, right? And this comes from the definition of your original ring Z of X. Z of X contains all polynomials with integer coefficient. So I found the range of our my homomorphism from Zx to Z. Okay, no other possibility. Or you can take any other ring that contains this one, but you'll have projectivity problems there. So I'm taking my homomorphism from Zx to Z. Okay. So after defining this one, to be sure, I have to look at the kernel, and I see that kernel 5, since I'm so clever that I can arrange it, kernel is equal to the ideal generated by X. And again, I know that this is surjective because I said it. Not said it, but said it. This is that. Okay? So after applying first isomorphism theorem, you reach the conclusion. Okay? Can I tell you the motivation in choosing a homomorphism? The reasoning why I can choose such an homomorphism, or how I can choose such a homomorphism. Özde, is that okay? Now a little bit. Okay. Any other problems? Okay. Any other problems? Any other questions?
Hocam benim var aslında.
Okay. Alta.
Constant term'ün neden olmaması gerektiğini çok iyi anlayamadım aslında.
Because here, this is just the definition of the ideal generated by something. Okay. Now, the given ideal here is the ideal generated by x. Okay. And this means that for an arbitrary element in an arbitrary ring, the ideal generated by A means that A times R such that R in R, right? For the ring R. Now here, this means that in this ideal, you have all multiples of X, okay? You have X and something in product, okay? So this means that, now where is it? Where is it? Where is it? Here. Here. Take an arbitrary polynomial, a(n)x and blah 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 a0, and if you multiply this arbitrary polynomial with x, then you reach an arbitrary polynomial with no constant term, because you're multiplying each term in the polynomial with x. So you don't have constant terms.
Anladım. Okay? Teşekkür ederim.
So defining homomorphism relates this fact with your homomorphism. Okay? So what about maximality? The first question was about this ideal being prime, and our answer is yes. What about maximality? Is it maximal? Just applying the theorem that we use here, since we take the quotient here, this quotient is isomorphic to an integral domain, and we know that that is not a field. So this means that the ideal generated by x is not maximal, okay? Question 2. This is again an application of the theorem. Okay, let me note it down. I is maximal if and only if R over I is a field. Okay, now what we know is that this quotient is isomorphic to Z, and Z is an integral domain, not a field. This means that since this statement is two-sided, meaning that I is maximal implies R over I is a field, and other way around, R over I is a field implies I is maximal. So since Z is not a field, this means that the ideal generated by X is not maximal. Okay, this is the application of the theorem, but you can do that directly by finding an intermediate ideal between the ideal generated by X and the whole ring. Okay, so let me write it down also. Find an intermediate ideal between this one. Intermediate means that it is an ideal and not equal to the ideal generated by X and the whole ring. Okay, so we need to find such an ideal. Consider the ideal generated by 2 and X. Not a principal, but 2 generated ideal. Okay, this is not the whole ring, right? And this strictly contains the ideal generated by X. So, since we can find an ideal between these two, This means that x, the ideal generated by x, cannot be a maximal ideal. Okay? Now, do you have any questions about maximal ideals and prime ideals? Hmm? Any questions? No? I don't have any. So, let me have a look at my questions. So, this one, show me, no. No, I don't have any more questions. So if you have some, you can ask, or if you have some problems with the subject, you can also ask.
Hocam ilk soru için tanımı kullanarak ya da teoremden mi yapalım diye bir soru sormuştunuz ya.
Which one?
En son yaptığımız sorunun ilk şıkkı için.
Okay.
Şeyden de yapabilir miyiz?
Just the definition. Okay. What was it? The ideal generated by x is a prime ideal. Okay, just using the definition. Here. The ideal generated by x is a prime ideal in that x and solution using the definition. Okay, now for this one, we need to take two polynomials such that the product of these two lies in the ideal generated by x. Let f and g be two polynomials in zx such that f of x times g of x lies in the ideal generated by x. Okay, now this means that being in this principal ideal means that f of x times g of x is h of x times x for some polynomial from the ring. Now, look at the right-hand side of the equality. You have the multiple x here. And this means that you can say 0 is the root of this polynomial, right? Polynomial h of x times x. So this means that since we have the equality, 0 has to be the root of the left-hand side. The other side of the equality. But 0 is root means that x minus 0 divides this polynomial, or the term x minus 0 must be inside one of these polynomials. X minus 0 divides f of x times g of x. Okay? So from here, since x is a 1-degree polynomial, x should divide f or should divide g. As x is of degree 1, x divides either x divides f of x or x divides g of x. Okay? And x divides f of x means that f of x is equal to x times sum h1 of x. And this means that f lies in the ideal generated by x because this is a multiple of the polynomial x. Or if this is the case, g of x is equal to x times h2 of x for some polynomial h2 of x. And this means that g lies in the ideal generated by x. Okay? So in each case, we have found that at first we took two polynomials, f and g, such that the product lies in the ideal generated by x. And at the end, we have found that one of these should hold. Either x divides, either f lies in the ideal generated by x, or g lies in the ideal generated by x. Hence, this ideal is a prime ideal. Okay? But here, of course, x being a polynomial of degree 1 is crucial. Okay? Because consider, instead of x, if we consider the ideal generated by, for example, x squared minus 1, generated by x squared minus 1. For example, take f of x as x minus 1 and g of x as x plus 1, right? Now, you're writing x squared minus, no. Okay, that's correct. Yes, x squared minus 1, you can write this one as f of x times g of x, but f of x is not in the ideal, f of x, which is x minus 1, is not in the ideal generated by x squared minus 1, and x plus 1, which is g of x, is not in the ideal generated by x squared minus 1. Now, this is because x squared minus 1 is of degree 2, and you can decompose it into polynomials of smaller degree. Okay, so let me complete it. The ideal generated by x squared minus 1 inside the same ring, containment, that x is not a prime ideal. We strongly use here that x being a polynomial of degree 1. Okay? Now this is the solution by just using the definition of a prime ideal. Is it okay?
Teşekkürler hocam.
You're welcome. Any other questions?
Hocam son verdiğiniz örnekte sesim geliyor mu bilmiyorum ama
Geliyor Serhat.
Yine verdiğiniz hani f ile g fonksiyonları birinci dereceden değil mi?
Yes, but the generator of the ideal is not of degree 1. So I use the fact that I can factorize the polynomial, the generator.
Ha, tamam, pardon.
Any other questions? No? Okay. Now that's all for today. If you don't have any other questions, if you have some, then after a 10-minute break, we can continue because we are running out of time for this session. Do you want one more session or something like 15-20 minutes to ask your questions? No?
Benim şu an sorum yok hocam. Yani kendi adıma.
Benim de yok.
Okay.
Quiz'in cevaplarını atacak mısınız yoksa?
Yes, I can do that. let me give you some time so that I can write down the solution and post on forum on OptiClass.
Tamam.